Hi there, all you cool cats and kittens, and welcome to Thermo Lab Rescue. Today, we're going to be learning about some distillation columns, and maybe even going to take you there virtually, since we can't go anywhere physically now. But as we move along, if you have any questions, just be sure to throw them in the comments section in Zoom, and we'll address them at the end. So, have a fun journey. So to start off, let's talk a little bit about the theory and background behind distillation. So distillation is largely dealing with the separation of components in a liquid mixture. And so the separation of these components is dependent upon the differences in the volatility of the individual components. What does that mean by talking about the volatility? The volatility is a measure of the vapor pressure of the individual component. So let's watch a little clip about vapor pressure.
Textbooks often state that when the vapor pressure equals the atmospheric pressure, boiling takes place. This is called the boiling point. Think of it this way. Atmospheric pressure pushes down, and that makes it difficult for the water molecules to spread out and form a bubble. But when the vapor pressure increases, molecules from the liquid escape, and they push against the air molecules and effectively reduce some of the pressure. This makes it easier for the liquid molecules to spread out, form a gas, and to rise to the surface. That's boiling. We can make boiling happen by either increasing the vapor pressure or decreasing the atmospheric pressure. Either way, once the vapor pressure and the atmospheric pressure are equal, we've reached the boiling point, and boiling can begin. One last thing. Different substances have different vapor pressures, and therefore they have different boiling points. This has to do with how strongly the molecules are attracted to each other in the liquid. The more strongly they're attracted, the less the vapor pressure, and it's more difficult to boil. Therefore, the higher the boiling point.
So two things that we can take away from that. One is that liquids with a higher vapor pressure will have a lower boiling point, and also that liquids will begin to boil whenever the vapor pressure equals the pressure of their surroundings. Most commonly, it's going to be atmospheric pressure unless it's being controlled.
Think about it. If you take water in a container and you allow it to start evaporating, the space above the surface of the water will start getting water molecules. That means it's a gas now, and gases impart pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away. So if you put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back in. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container. And that pressure is called the vapor pressure of that liquid. In the case of water, you would say it's the vapor pressure of water. It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happening, but in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate, so there's no net change, but you have established what we call a vapor pressure.
So now we need to explore the equilibrium of vapor pressure for a mixture. When dealing with mixtures, the vapor pressures of the components are no longer the same as when they're in their pure component form. This is due to the various intermolecular forces or interactions that occur between different components. When dealing with distillation, the component with the higher vapor phase is called the lighter component and has the lowest boiling point. And the component with the lower vapor pressure is called the heavy component and has a higher boiling point. In a binary mixture, the lighter component becomes the driving force for the vapor-liquid separation, since it's more likely to evaporate due to its higher vapor pressure. And since your assignment 2 is focused on separating water and ethanol, here's a clip that might help better connect this information.
If we place a bowl of the mixture inside a closed container, molecules of both water and ethanol will enter the vapor because of the vapor pressure of each component. At equilibrium, how much of each component will be in the vapor mixture? The answer depends on the relative vapor pressure. Since the vapor pressure of ethanol is higher than water, ethanol is more volatile than the water. Therefore, ethanol molecules will want to escape from the liquid in a higher ratio than water. At equilibrium, the concentration of ethanol in the vapor will be higher than the concentration of ethanol in the liquid mixture. Since the vapor has a higher concentration of ethanol, the liquid must have a lower concentration than before any of the ethanol evaporated. As a result, the liquid has become less concentrated in ethanol. The vapor pressure of each component in the mixture will change with the concentration of each component. This means that the composition of the vapor mixture in equilibrium with the liquid mixture will change depending on the liquid composition. We can measure the vapor composition in equilibrium for a number of different liquid mixture compositions. The result is the equilibrium curve. The equilibrium curve for water and ethanol is shown for different ethanol concentrations. If the fraction of ethanol molecules is 0 in the mixture, the liquid is pure water, and the fraction of ethanol in the vapor is 0. If the fraction of ethanol molecules is 100% in the mixture, the liquid is pure ethanol, and the fraction of ethanol in the vapor is also 100%. For all of the mixtures in between, the equilibrium curve tells us what the vapor concentration is. For the example on the previous page, this curve will tell us what the vapor concentration of ethanol is. Recall that the liquid mixture is 25% ethanol and 75% water. If we find this point on the curve, we see that the concentration of ethanol in the vapor is 56%.
Well, there you have it, folks. The theory and background leading up to the equilibrium curves plays a major role when we're dealing with our distillation models. So, moving forward, let's talk about distillation columns themselves, beginning with a little batch distillation. Woo! That was a fast trip to the unit ops lab. Hey, thanks for joining me in the Prescott 101 unit ops lab. Now, the first thing we want to make sure you do when you're going to a lab like this is that you have the right PPE on. Notice the hard hat and the glasses. Can't see, I got my boots on, closed-toed shoes. And so you may need more depending upon what type of chemical or experiment you're trying to do. So make sure to plan accordingly. Now, as you can see behind me here, we have one type of distillation column, but there may be several different ones you'll encounter in your time as a chemical engineer. So let's talk about those real quick. So one distillation setup that many of you have probably already encountered in either organic or maybe even general chemistry labs is a batch distillation setup. And so with this one, you have your primary reservoir right here, which already contains your feedstock. And then as heat is applied to that feedstock, your lighter component will begin to vaporize off, traveling up this tube. And as it reaches in here, the condenser will begin to cool that back into a liquid so that it can collected in this vessel over here. Now, where this may sound efficient, there is one large drawback, and that's that you only have one equilibrium stage to this entire system right here. And so you really don't reach as pure of a product as you could as if there were multiple stages on here. So as I mentioned, when looking at a batch distillation or a flash distillation, which is more like a continuous process of the same thing, but there's still only one equilibrium stage, in order to get a more pure product, you have to take whatever you distill off and put it back into another batch distillation, which will have a higher concentration of the lighter component. And so after another equilibrium stage, we'll continue to get more pure and pure products at the end, but that can be a very time-consuming and energy wasteful process. So let's check out a video about how this may relate to a full-size distillation column.
Let's look at the sequence of steps on the equilibrium diagram for ethanol water. Suppose the initial ethanol-water mixture is 25% ethanol and 75% water. The ethanol concentration of the vapor of this first stream is 56%, as we see on the equilibrium curve. If we condense this vapor to a liquid and feed it to a second pot, the liquid mixture is also 56% ethanol. What is the concentration of ethanol in the vapor in the second pot? We can find this easily on the equilibrium curve by using the 45-degree line. Remember that the 45-degree line is nothing more than the points where the vapor and liquid concentrations are the same. If we draw a horizontal line from the equilibrium curve to the 45-degree line, this point now represents the liquid mixture in the second pot. By drawing a vertical line up to the equilibrium line, we can determine what is the ethanol concentration in the vapor in the second pot. The concentration is 68%. What about the third pot? We draw the horizontal line to the 45-degree line and the vertical line to the equilibrium line and find our answer, 75%. This procedure can be repeated for any number of pots. Each one of these steps is called a stage. It takes 3 stages to produce a product with an ethanol concentration of 75% from a liquid mixture with an initial ethanol concentration of 25%. Instead of using a sequence of pots, we can essentially do the same thing in a distillation column. A distillation column is nothing more than a series of pots stacked on top of one another with continuous flow from one pot to another. Each of these pots are also called a stage in the column. In practice, the separation is either done with trays or packing instead of pots. We can think of a tray or a certain height of packing as a stage in the process. The distillation column is a continuous process. It has a feed stream containing the original liquid mixture. From the top of the column, the distillate containing the more volatile components is removed. From the bottom of the column, the residue containing the less volatile components is removed.
So now that we have a little bit of an idea about distillation and how that relates to the equilibrium curve, let's check out a tutorial on a full-size operating distillation column. Take note, this one is sort of beginning from the start, so I will provide commentary, sort of help explain the process. So you can see here is a structure of a rectification. This main area in the center is the rectifying section. And the first thing we're going to look at is the preheater to the feed steam, where you can actually heat your feed to a desired temperature, which will be important later. And this is the actual rectifying section of the column where the true separation takes place. And this is your bottoms cooler. So whatever you have coming out of the bottom of the distillation column, you may not exactly want at that temperature. So you got to cool it down. And this is the distillate condenser. And so here is where we condense that vapor back into a liquid phase. At which point you may want to cool that further to in your distillate cooler over here. And so this one is your reboiler, or in German, your circulation evaporator, where your bottoms is converted into vapor. So it flows up through your rectifying section to the top all over again. So what you see here are control valves. So you have final product control valves and then inner reflow or reflux control valves. What you can see highlighted in green is your coolant flow throughout the system. The first one we'll look at is the feed stream into the column. And so when that one opens up, you have your feed stream flowing into your heat exchanger. That heat exchanger is filled with a heating liquid, indicated in your red there. And then that heated feed is going to flow into your column at some specific desired feed tray. And as you can see here, depending on where you feed it in, your feed slowly fills up each tray before it moves on into the next one. This happens to each successive tray. Now, as I mentioned, we are in the process of starting up our column right now. So there's a few specific things that you'll want to do whenever you do this. And so the first of those would be to open that flow control valve at the bottom, so you don't have a buildup of liquid in your column, because that could cause hydraulic pressure to build up as things overfill and vapor can't get through. It could lead to an explosion. So this way your system remains open, and you can see your reboiler or your evaporator, whatever you want to call it, on the side there, is fluid level is equal with that of your bottoms. Just to note, everything below that feed line is considered your bottoms, and everything above is your rectifying. So you can see in your reboiler here, as you apply energy to it, your bottoms is converted, the lighter volatile component becomes a gas, is vaporized, and it flows up through your column through those full trays, which we'll talk more about that later, into the upper part of the column. So your lower and upper. And then that vapor enters into your condenser for your distillate, which has coolant flowing through it and condenses that vapor back into a liquid, which you can see right now, based upon this control valve, we have set to full reflux. The purpose of that is because as we're starting this column, we want to refill, or we want to fill the trays at the top so that every tray is coming in contact between the liquid and the vapor. Again, we'll explain the importance of that as we move on. And so everything that we've talked about so far is really just looking at the mass flow throughout your column. So remember, mass flow is only one part of the whole equation. We still have a whole energy side of it, which is quite interesting when you look at it. And so where we have that first heat exchanger there, heating our liquid to or our feed to a desired temperature. Oh, you can see the full flow there. You have an initial temperature and then your feed temperature. And so that sort of sets the very initial sort of temperature distribution, your temperature profile of your lower column. And then as energy is added through the reboiler and that lower or lighter component is vaporized, then as that hot gas or hot vapor enters your column, you can see that it's going to change the temperature distribution of that lower part. And it'll also, you can see, affect the upper part. So then the rate of energy removed by your condenser, it determines the temperature of the reflux stream and temperature of the profile stream of the upper column, as you can see here. And your reflux ratio is also a large contributor to that, because as the reflux is changed, so that means that you have less of your condensed vapor returning to the column, you actually have some of it leaving as distillate, then it's going to shift that temperature profile. So as you can see here, your liquid mixture contains both of the components, and the tray, as the vapor rises through the bubble caps, the vapor must travel through the liquid mixture to further increase your vapor-liquid separation through the differences in temperature and volatility of the components. So as your hotter vapor phase will heat the incoming liquid phase as it bubbles through the tray, evaporating the lighter components to leave with the vapor phase, the cooling properties of the liquid phase will cause the heavier components from the vapor phase to condense and exit with the liquid phase. So in your trays, that's really where the separation purifies. So it's a pretty quick animation or brief overview of a distillation column. Again, that is a continuous distillation column. But let's look into a few of the more specific parts of it, shall we? Generally, for a binary mixture, you can use a McCabe-Thiele diagram to model your distillation column. This type of diagram is useful for determining the minimum number of trays and feed stages for a particular feed stream and or distillation purity. So on your y-axis here, you have your molar fraction of the lighter component in the vapor phase. And on your x-axis, what's represented by y. And on your x-axis, you have the molar fraction of the lighter component in the liquid phase, represented by x. Now to break down the McCabe-Thiele diagram, first off, you have your 45-degree line here, which is essentially represents whenever the species is an equimolar composition between the liquid phase and the vapor phase, the lighter component. And you have your equilibrium curve up here for the binary mixture. And so the first thing we'll look at is the mole fraction of the lighter component in the feed stream, represented by XF. And so by plotting XF on the McCabe-Thiele diagram, and find where it intersects that 45-degree line, as you see here. And then we're going to look at the liquid mole fraction of the lighter component in the bottoms coming out of the distillation column. And we're going to also graph it onto the McCabe-Thiele diagram where it intersects the 45-degree line. And thirdly, we're going to look at the liquid molar fraction of the lighter component in the distillate stream, and then map it on the McCabe-Thiele diagram. And so this is essentially our desired purity of our distillant, which we set right here. And this is what we control from the feed stream. So moving forward with our operating lines, first one we look at is the rectifying operating line, which is determined by the upper part of the column there. And so with the equation I'll show you here in a minute, you're able to draw this rectifying operating line starting at the composition of that lighter component in the distillate stream. Next, we're going to look at our Q line. So the Q line is determined by the phase of the feed stream. And so that is represented on the McCabe-Thiele diagram beginning at your feed composition of the lighter component and then drawing the Q line out based upon whether or not, well, we'll say first where this Q line intersects your rectifying line, that's where your feed point is going to be for your distillation column. Now this Q line is dependent on the phase of the feed line, and as that changes, for instance, when you have a saturated liquid, your Q is equal to 1. And when you have a subcooled liquid, your Q is greater than 1. And if your feed stream is a saturated vapor, your Q would be 0. And anywhere in between there is going to be a liquid vapor mix. You could also have a Q line below 0, and that's going to be a supercritical vapor. And you're more than likely this line will be coming straight down through here as well, changing everything. And so once we have that, then the stripping operating line is really easy because essentially you're taking this composition of the lighter component in the bottoms and you're drawing a line that intersects with this feed stream, pretty much like so. And there we have our McCabe-Thiele diagram with our operating lines added on, and we know where our feed stage is, we know where our bottoms are, we know the desired purity of the distillate stream, and so we can begin drawing our stages on here. And we do this initially, our boundaries are the equilibrium line and our rectifying line. And then once we cross this feed line right here, then our boundaries change. And now we have we'll be bound by the equilibrium line and the stripping line. But as we continue to draw, we'll note that this stage where the feed line was crossed now becomes our feed stage. And then once we cross this bottoms line down here, or the composition of the lighter component in the bottoms, then that is where we will end our stair steps, and that becomes our reboiler stage. So with this, we have 4 complete stages with the 5th stage in the reboiler stage. And if we were to change our desired purity of the distillate stream, if we were to shift it up, then we would obviously have more stages happen here. Or if our Q line was to change, be up here, then everything would change as well. And then also, if you were to change your feed composition, things would change. So you have several different options there. And so now to look at how those lines, operating lines, are calculated, we'll break it down just a little bit. Obviously, so these are the equations I provided for you. We're not going to really go into their derivation right now, but I will provide the information for it. But that's sort of the math that goes on behind the McCabe-Thiele binary distillation model Excel file that I sent you, if you're really interested. So just looking at trying to tie this together with sort of the concepts that you learned in class with the different plates. And so here you have your feed section. Here you have your rectifying section with this equation, which I'll state that your R here is essentially what's returning over what's leaving the product streams. And this right here would be your L. And then you could say, because these are going to be the same, so it's a D over there. Oh, there we go, underneath. And down here you have your equation for your stripping line, and that follows your bottoms coming out down there, and then your L prime coming in, all that. And you can notice all of these equations are essentially set up in the form of Y equals mx plus b. I'm running with the mouse, so not the prettiest, but it's it across where each of these first little parts here, those are your slopes, so those are your m's, and these whole second ends right here are essentially your y-intercepts, because these things, like your the molar fraction of the lighter component in the distillate stream is a constant, and it'd be a constant here as well. And this right here are given essentially. So there you have it, your McCabe-Thiele diagrams broke down in the different components. So the last major thing we're going to look at is going to be the unit ops lab. So as you can see here, we have as you walk up the unit operations lab at the distillation column, you have your computer here to measure and record your temperatures, and the main distillation unit over here. And a little bit of a closer look. Next to your distillation column, you have your collection unit here. You have a smaller one above it if you're waiting, but then there's a valve you turn here and flows in, and then your valve right here is out. There's also a valve down here at the bottom of this vessel for draining your bottoms out of it. So one of the first things you're going to do when you're operating this distillation column is you're going to want to turn on your condensate flow, so the cold water to your condensers. And so you're going to want to keep that between about 40 and 50, and it's PSI on there. But you read that with your rotometer right here, where this flat edge is the level that you are at. And so the condenser, so you can see closest, is at the right above the final collection bin. You have a little tiny one here, and there's a few valves that turn it. You can see it flowing in and flowing out. Flowing in, flowing out. Be careful not to turn it up too fast, because there's going to be some air in there that you want to take out. And here's the larger condenser unit at the top of the column. And you have it here flowing in and flowing out. So at the base, once you have your cold water flowing, you can feel your unit. Now probably the easiest way to do this is at the top with whatever your mixture needs to be. And so if you're filling up with water, you can connect the cold water source over here and just fill it down through until your water gets up to your reboiler right here, where it's nice and see a little bit out. So as it's heating it, you'll see the flow come through, you see vapor, it starts to go up. And just a little reference here, you can see how tall or how high up you are when you're at the top of this unit. So you definitely want to be safe here and not take any undue risk. And so once that's all done and you have everything ready, you turn on the steam, which is if you're walking in the lab, it's in the upper left-hand corner above the dry chemicals room. It's this main valve right here. And then the steam comes into the distillation unit through these pipes behind it, and you control the PSI right here. Make sure to stay within the bounds of the user manual that's located there. And that steam is transferred then to this reboiler unit, which the bottoms come out and around and up through here, where it's then heated, and then your vapor, your lighter component vapor, goes up through there, through the column. And on the computer, you can monitor the temperature of the column, the distribution, as it flows up, as your vapor flows up, heating the column. And you can see the temperature of your distillate streams and your reflux streams. So heading up to the next level, you can see more closely this second distillate condenser over here. You can also see the trays of the column. You can see each unit here. The bubble cap trays that are on there. So each one of these is considered an equilibrium separation stage for the distillation column. And then with your you can also see the main distillate condenser up here, so which is cooling that heated vapor as it comes up. And then as it condenses, it comes back down to this reflux unit right here. And then which you can determine how much reflux you want to go into your distillate stream and how much you want to come back into your tower, your column. And there's a closer look at it. You can see right here where this is the unit that's determining how much goes in and how much goes out. And this motor that here is controlled a unit on the wall behind the distillation column. So this switch right here turns it on or off, and the switch between full and partial reflux, you can use this hand and auto right here. And so in the trays at each stage, the type of unit or the type of plate that's being used uses bubble caps. And so when your air is coming out, it'll come up and over through here. Your liquid levels, probably about right through here. It's at right below this cap line. So any air coming out or gas vapor coming out has to go up and out through there. You can see here perforations. Even another demonstration of it. Come out like that. And yeah, that's a quick rundown of the distillation column in 101. Well, I hope you all have enjoyed this little lesson on distillation columns and theory and have taken away a little bit of information that you can apply later on. So that's the end. Remember, stay safe, stay apart.